So 2.58, investigation, stretches of functions. So what we're going to do is we're going to complete the table of values below for the function f at x equals x squared. So that's just our parabola, okay? And then what we're going to do is we are going to apply this 2, and then we're going to apply this 1/3, okay? So our normal parabola is 4, 1, 0, 1, 4. Okay, we know that it's going to go through -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. Okay, so that's going to be our normal, our like base function. I wanted to extend it to the 3, 9. I know it goes through like 3 and -3, 9. Just so that when we draw the other two, it's a little bit more accurate. Now, if we were to take these numbers and actually sub it into this, what's going to happen is we're going to go to 8, 2, 0, 2, 8. And this is just math. Like, you can go to the side of your paper and say g at -2 equals 2 at -2 squared. Okay, 2 times 4, and that equals 8. So you're able to just sub those in using function notation. So let's graph that one. -2, 8, -1, 2, 0, 1, 2, 2, 8. Okay, and I'm just color coordinating these instead of writing all over the graph. A little bit different of approach. Okay, and now this time we're going to do 1/3 x squared. So again, if we had h at -2, we would do 1/3 -2 squared. So 1/3 of 4. So 4/3. Okay, so this is going to be 4/3, 1/3, 0, 1/3, 4/3. Okay, so that one's going to look like this. So B says graph the above 3 functions on the same set of axes, which is what we just did, and I use different colors to label them. Okay, are these congruent in size? So up until now, we've seen everything is like the same actual size. It's just shifting around or flipping over. In regards to this one, this is not the same size. So no, it's the same shape. They're all parabolas, but they're not the same size. So let's take a look at their domains. So I'll do green for f at x. So I'm going to write domain first and then range. So we have XER, that didn't change. And we have YER such that y is greater than or equal to 0. So that didn't change. We did not shift it around. So this vertex point here actually did not move. So 0, 0 is still our reference point. All we did is like stretched or compressed it. Okay, for blue, XER still, nothing changes with that. And YER such that y is greater than or equal to 0. Okay, and for the last one, XER, and we have YER such that y is greater than or equal to 0. Okay, so all of these have the same domain and range. The lowest point here is 0. It goes up forever, left and right forever. Okay, so when we take a look at this, how would we actually describe what's going on? And remember, oh, I reversed these colors. This one was supposed to be blue. It's okay. Okay, so from the original, and I'm just going to write in this blue. From the original, if we had 2x squared, see this green graph here compared to the blue graph? It's getting taller and skinnier, so it's increasing faster. This is a vertical stretch. Okay, and when we're talking about a third, compared to the blue, the maroon is like pushed down more, right? It's going, it's increasing so much slower. So this is a vertical compression. Okay, so we're going to do the same idea, but for the root x function. So in the normal, in like the base function or the parent function, the points are 0, 0, 1, 1, 4, 2, 9, 3. Okay, so if we did g at x equals 3 root x, then we're multiplying every single y by 3. Okay, so 0, 3, 6, 9. And if we did the same thing for h at x, except for with a quarter, we would have 0, a quarter, 2 quarters, which is a half, and then 3 quarters. Okay, so I'm going to go ahead and graph these, 4, 2, 9, 3. So I'm going to graph the original f at x in blue. G at x, I'm going to color coordinate with green. So 0, 0, 1, 3, 4, 6, and then 9, 9. Okay, so that's going to be our g at x. And then I'm going to do the last one, h at x, in red. So 0, 0, a quarter, 3 quarters. Oh, that's a half, and that's 3 quarters. So this is going to be h at x. Okay, so are these congruent? Well, no, they're not congruent in size. They are all root x shapes, but even the shapes aren't congruent because they have stretches and compresses on them. Okay, domain and range for each function, if you think about it, we all have, every single one of them has this starting point, which is like 0, 0. And all of them, because they're not reflected, they all go to the right forever, and they all go up forever. So for the normal root x function, XER and YER, such that x is greater than or equal to 0, y is greater than or equal to 0 as well. Okay, for g at x, it's going to be the same thing. Even though there was a stretch, it's not opening a different way, and it didn't move up or down. So we still have that 0, 0 as our starting point. Okay, and for h at x, we're still going to have XER such that x is greater than or equal to 0, and YER such that y is greater than or equal to 0. So if we actually thought about what was going on, if f at x is our base function or our parent function, vertically, g got stretched up. Okay, so this is a vertical stretch. Okay, and 1 quarter, this got closer and closer to this x-axis, so it got like squished down. So this is a vertical compression. Now we're going to do the root x function again, but this time we're going to insert numbers under the root sign right beside the x. Okay, so again, for the original root function, I have 0, 1, 2, 3 as my y values. Okay, so 0, 1, 1, 4, 2, and 9, 3. Okay, so for g at x, we're going to go root 2x under that root sign. Okay, so if we put g at 0 equals root 2, 0, the root of 0 is just 0. Okay, and then if we put a 1 in there, we would have root 2, which we get like 1.4. Okay, so 0, 0, 1, 1.4. If we had a 4 in there, it'd be like root 8. So we'd have 2.8. And then if we had a 9 in there, we'd have root 18. So then we'd have 4.2. 2.8 and 4.2. 2.8 and 4.2. So here is our g at x. Okay? And then the exact same idea for h at x. We have 0. We'd have root of a third, which is 0.6. I'm just going to round. We'd have root of 4/3, which is 1.2. And then we'd have root of 9/3, which is root 3. We have 1.7. Okay, so let's plot that too. 0, 0, the same thing. 1.6, 4, 1.2, and then 9, 1.7. Okay, and then this is h of x. So are these congruent? No, okay, because they're getting stretched here or compressed. So let's do the domain. So the domain of the original is always going to be XCR such that x is greater than or equal to 0 and y is greater than or equal to 0. Okay, this 0, 0 point is common between g at x, f at x, and h at x, so all of them. Okay, so actually all of the domain and ranges are going to be the same. Okay, they're not reflecting, so they're still going to open, like go up forever and then to the right forever. Okay, this is where it's a little bit backwards though. So let's pay attention to this. F at x is the base function. G at x, if we're talking about, let's talk specifically about horizontal, okay? So we're going to describe these, because it's under the root sign with the x, we're going to describe these as a horizontal. Okay, so horizontally, so when we talk about it getting closer or moving further away from this y-axis, from blue to green, it's actually compressing in, right? So we're not talking about vertical this time, we're talking about horizontal. So we're talking about it's getting closer to the y-axis. So the g at x is a horizontal compression. Okay, whereas if we're going from blue to red, red is getting away from that y-axis. So again, when we're talking horizontally, this is a horizontal stretch. So now we're going to complete the table of values for 1 over x, the 1 over x function. Okay, so we only need two coordinates. We need -1, -1, and 1, 1, and that's from the original. Okay, so from the original, we're going to have a vertical asymptote at x equals 0, and we're going to have a horizontal asymptote at y equals 0. Okay, now if we were to plug this in, what we're going to get, let me do this in green. Okay, so we're going to go 4 times 1 over x. So we're going to get -4, -4. This is -1, -4. We're going to sub the 1 in, we're going to get 4, sub the 4 in, we're going to get 1. Okay, so I just extended it, but we don't have to on test or anything. We just need these two coordinates here. And there are no shifts, so the vertical and horizontal asymptotes stay the same. Okay, so the original would have looked like this, and we only really need those 2 points to see what quadrants it's in. And I want to make that a little bit more smooth. Okay, so now we have -4, -1, and -1, -4. Okay, so again, in this quadrant again, it's just going to look like this. And in the same quadrant, it's just going to look like this. Okay, now h at x. So we're going to have 1/3 times 1 over x. So if we subbed in negative 1/3 for x, we're going to get negative 1. If we subbed in negative 1, we're going to get negative 1/3. If we subbed in a third, we're going to get 1. And if we subbed in 1, we're going to get 1/3. Okay, no shifts, so the asymptotes don't change. So we get negative 1, negative a third. Okay, so these are plotted here. So see how this is getting closer to the axes? Okay, so we graph them all. They are not congruent. So domain and range actually don't change for these. Okay, no matter what, x is not going to hit the vertical asymptote, and y is not going to hit the horizontal asymptote. Okay, then green, same thing. X is an element of the real number system such that x does not equal 0. Y is an element of the real number system such that y does not equal 0. Okay, and for the red one, the exact same thing. Okay, the restriction on the domain and range are always the horizontal and vertical asymptotes. So if we looked at this, I'm going to quote this. I always quote this as a vertical transformation, okay, because I take the 4 out of the 1 over x, or I take the 1/3 out of the 1 over x. So in regards to the 4, if we took a look at the green function, it's getting further away from the x-axis faster. So that's a vertical stretch. And if we took a look at the red, that's getting closer to the x, well, and the y-axis. So that's a vertical compression. Okay, so just as an overview, here's a conclusion. If we have a vertical stretch, the number is here in front of the f at x. Okay, so if that number is greater than 1, we have a vertical stretch. And if that number is like a fraction between 0 and 1, then we have a vertical compression. Okay, in regards to these, ignore the negative sign. Okay, the negative sign is a reflection. Okay, so we already took care of the reflections, so treat them as 2 different transformations. The negative sign is going to be a reflection. The number is going to be either a stretch or a compression. Okay, and for horizontal, whatever number this k is, if k is greater than 1, it's actually a compression by 1 over k. And if k is like a fraction, it's actually a stretch by 1 over k.